Now, you might have realized that this particular question that I gave you, 35.517 with a Z, is actually referring to element of chlorine. And you might have derived the number of neutrons as 18.5. This decimal of 0.5, do you think it actually makes sense? Shouldn't the number of subatomic particles be a whole number? How can there be half of a neutron? And actually this comes about because of this concept known as isotopes. So now we are going to explore this concept of isotope by considering a few factors. What exactly is an isotope? Over here I have 3 examples of hydrogen atoms. These are all hydrogen atoms, take note, but if you notice, there are certain differences between them and certain similarities. Can you identify what are they? All of them have the same number of protons, which is 1. They also have the same number of electrons, which is also 1. So what exactly is the difference? The difference is in terms of the number of neutrons. In the first one, there's 0 neutrons. In the second one, there's 1 neutron. There's 2 neutrons. The term that we use to describe such atoms are isotopes. So isotopes are atoms of the same element with the same number of protons and electrons but a different number of neutrons. So everything else is the same except for the number of neutrons. So as a result, the nuclear number will be different from all these atoms. Okay, so you can see over here for hydrogen, the nuclear number that's represented at the top, okay, they're all different because of the difference in number of neutrons. For chlorine, similarly. Alright? So, what exactly is the mass number of these atoms? The mass number of these two are 35 and 37. But if you take a look at your periodic table, the mass number of chlorine is actually 35.5. So why is it neither 35 nor 37? Could it be that chlorine actually has half a proton or half a neutron? And that's not possible. This is because for elements with isotopes, the mass number that you see is actually calculated based on the relative abundance of each type of atom. What do I mean by that? So because there's 2 types of chlorine atoms, chlorine isotopes, right? In reality, there's 75% of them exist as chlorine 35, which is this one, and the other 25% in the natural world exists as chlorine 37. So how do we calculate what exactly is the mass number? We actually do a simple mathematical calculation based on the relative abundance of each isotope. So the mass number of chlorine will be equivalent to 75% multiplied by 35, which is the mass number of this chlorine 35, followed by 25% multiplied by 37, which is the mass number of chlorine 37, and you end up with the value of 35.5. Let's take a look again. With this formula itself, the mass number is equivalent to the percentage of a particular isotope multiplied by the mass of this particular isotope, adding on to the percentage of another isotope multiplied by the mass of the other isotope, and adding on to whatever number of isotopes there are. So for chlorine itself, because there's 75% of them as chlorine 35, this is the calculation. 75% is actually 75 over 100 multiplied by the mass number, and then we'll add this on to 25% multiplied by the mass number of 37, and this will give us the value of 35.5, and that's how we derive the mass number for chlorine. Let's try out another example. Suppose you have carbon, which consists of 98.93% of carbon 12, 1.07% of carbon 13, and a small amount of carbon 14. What exactly will be the mass number? So similarly, let's do a quick calculation. If you have 98.93% of carbon 12 and 1.07% of carbon 13, how many percent will be this trace amount? If you do the math, it's actually almost 0. So this carbon 14 itself will not affect the relative atomic mass. Then now let's do the calculation. 98.93% of carbon 12 added with 1.07% of carbon 13. Right, do the math, this will be equivalent or close to 12. And that's why for carbon itself, if you look at the periodic table, you realize that the mass number of carbon, or in other words, the nuclear number, is equivalent to 12. Now, that's the calculation itself, but how do we explain it if the question were to ask us to do so? Over here, you'll notice that there's a model answer provided for you to take note of. So the mass number of chlorine is 35.5, and you're asked to explain why it's not a whole number. The explanation, there's actually 3 parts to it. First, because chlorine occurs as a mixture of isotopes, and to be more exact, there's 2 possible isotopes. Right? So this 35.5 that you see is actually a result of an average of the relative abundance of each of the isotopes. And that is how you should structure your explanation in a structured questions. Now, isotopes, besides having similar protons and electrons and different neutrons, you might be wondering, why exactly am I learning about isotopes? Right? So isotopes actually have very interesting properties. So they have the same chemical properties, but they have slightly different physical properties. The reason why they have the same chemical properties are due to them having same number of valence electrons. Okay, at this point in time, you wouldn't learn this term yet. So what exactly is valence? Valence just means the outermost electrons. Okay, not to worry, we'll cover this at the later part of this chapter. Alright, however, your isotopes actually have very different physical properties. Let's take for example 2 different isotopes. Hydrogen, like what I mentioned just now, there can be hydrogen 1 and hydrogen 2, which is known as deuterium. Okay, this is the same as deuterium. Okay, so based on that, what do you think will be the properties? What's going to happen is that in this video, they actually made ice cubes based on the 2 different isotopes. One is based on the hydrogen 1, the other one is based on hydrogen 2. Which one do you think will have a higher density and which one will have a lower density? Make a quick prediction now. Alright, and now I'm going to show you the video. I want you to observe what exactly happens, and I want to come up with some form of explanation for why exactly is it in this manner.
Heavy water. Heavy water is also known as deuterium oxide. It is used in chemistry as a source of deuterium, as a solvent in NMR spectroscopy, and as a coolant in special nuclear reactors. In standard conditions, it has its boiling point at 101.4 degrees C and freezes at 3.8 degrees C. Heavy water has a slightly higher density than ordinary water. That's why ice cubes out of heavy water sink in ordinary water. An interesting effect is that trapped gas bubbles cause the ice cube to float after a while. Hydrogen has 3 isotopes: the well-known protium, the heavier deuterium, and the radioactive tritium. Tritium oxide is also called superheavy water.
As you can see in this video, the ice cube that is made out of the isotope of hydrogen 2, deuterium, actually sinks. Okay, it sinks. So, whereas the other one, which is a normal ice cube that you see on a daily basis, it will float as expected. Right? So what exactly causes the difference between them? Now, your isotopes will have different physical properties because of the only difference between them, which is the difference in relative atomic mass. This will result in very different physical properties such as densities, melting and boiling points. If you look at these 3 examples, because they form 3 different compounds of water over here, these are all water compounds, but because they are made of different isotopes, they will have different densities. So this will be the least dense, this will be slightly denser, and this will be the densest, simply because they have very different relative atomic mass. In terms of melting and boiling point, the heavier the isotopes, the higher the melting point and boiling point itself. Now, Isotopes, they actually can emit high energy radiation and are harmful as it can damage living cells and cause cancer. For instance, your barium-137 as well as the iodine-131 are radioisotopes that emit gamma ray. Okay, obviously it's not going to make you become the Hulk, okay, but they are able to release high energy radiation. But if you were to put it into good use, good and safe use, radioisotopes actually have very useful applications. For instance, it can be used to determine the age of fossils, to treat cancer, to be used for nuclear imaging, to be used for nuclear energy. Alright, all these are just a few applications of isotopes if you were to use it correctly.